The pin adds noise, and one source of noise I mentioned is the thermal noise. And again, this is thermal noise, which we find in all electrical receivers. It's the classical additive white Gaussian noise that's modeled as a flat power spectral density. Okay, and it has a Gaussian distribution. It's flat, which is where we get the name, the acronym AWGN. The level of the power spectral density, we'll call in the noise level for thermal power, is given by the classical thermal noise, which is 2 times the Boltzmann constant, temperature divided by the load resistance. And the power spectral density, which I'll call S thermal, as a function of F, is constant for all F. Of course, no device has infinite bandwidth. In fact, the F, I guess we could say, for all F within the bandwidth of the PIN. Certainly we can say that the thermal noise is very well modeled as flat over this bandwidth. In fact, that's sort of the definition of what the bandwidth of a photodiode is. In most cases, electronic receivers will have a narrower bandwidth than the photodetector. So typical systems will take our signal, comes in, it goes into a PIN, but then we'll also put in an electrical filter to limit this wideband noise and only let in an amount of noise which is necessary. And so our electrical filter will have a bandwidth of its own, and this bandwidth will be selected so as to not cut off the signal, but to cut off as much noise as possible. So what I would characterize this electrical filter as, we'll just put its impulse response, not impulse, transfer function. We'll call HE of F, the electrical transfer function. And there's a definition, which I guess I'll go into really on Thursday, the formal definition. But for right now, there's a equivalent bandwidth which is a measure of the width of the filter, which is not dependent on the filter shape. So it tries to, although the filter HE of F may have a particular shape in the frequency domain, the equivalent bandwidth, the noise equivalent bandwidth, in fact is what we usually call it, noise equivalent bandwidth, reduces the filter to one characteristic. In this case, the typical system, we would try here, our signal comes in, it's a PIN photodiode. It gets filtered by an electrical filter. We have the received signal, which is continuous, and then we're going to sample it. So this is sampling in order to get a decision statistic, which will be based on signal plus some noise. So after passing through, so this PIN creates thermal noise. The electrical filter limits thermal noise. And now the sampler creates a digital sample, or a single sample, of the continuous time random process, which is additive white Gaussian noise. And all that to say that the noise sample that we see here at the output of our receiver has a variance. So the noise variance of the decision statistic after the sampler is given by sigma squared thermal is just equal to the power spectral density of the thermal noise times the noise equivalent bandwidth of the front end, the electrical front end. What will be, clearly this is Gaussian since the noise is Gaussian and the filter is linear. So we have a linear manipulation of a Gaussian process, so this is also Gaussian. So we would say that the thermal noise has a Gaussian distribution, which is zero mean and has a variance. So this is a notation I will be using. This script n refers to normal or Gaussian. And the first argument is the mean. Second argument is a variance. And the little tilde means is distributed as. We will have a collection of noise samples, one at each one of the sampling intervals. In fact, what we'll be talking about on Thursday is a brief review to remind you that if a Nyquist filter is used, the noise samples will be uncorrelated. And of course, for Gaussian random variables, uncorrelated equals independent, which allows for the bit error rate analysis. Okay, so very straightforward. I'm sure you've seen this all before.